Okay, we're going to find the limit of this rational expression. Notice what we have is we have a binary expression raised to the third power. And really, most of this problem comes down to simply using the formula for the expansion of a plus b to the third power. Now, that formula is a to the third, a plus b to the third power is a to the third, plus 3a squared b plus 3a b squared plus b to the third power. The pattern that we see is we start off with a to the third. Well, it's a plus b to the third power, so we take that 3 as a to the third, then a squared, a, then a to the 0. So a to the third, a squared, a1, a0. Then we don't see a b, but you could say b to the 0, b1, b2, b3, b cubed. Now, the coefficients are 1, 3, 3, 1. That comes from, or one way to find those, is by using Pascal's triangle. So that's a little review right there. How do you find the coefficients of binomial expansion? You use Pascal's triangle, where how that works is you put one along the sides. It sort of looks like a little tree or something. Notice that 1 plus 1 makes the 2. Sort of ruined it by putting those lines there, but I'm trying to direct our attention somehow. The 1 plus the 1 makes the 2. 1 plus the 2 makes the 3. 2 plus the 1 makes the 3. That's how we go to the next line. If you wanted to go one step further, you would follow along that same pattern and get 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, 1. It's not really the topic of this video, but we need to use this formula for the expansion a plus b to the third power. All right, so let's go ahead back to the limit and expand where we have. So again, Pascal's triangle gives us Pascal's triangles gives us the coefficients for the expansion of a binomial. 1, 3, 3, 1 is what we get with this expansion, 1, 3, 3, 1. Okay. Now, x plus h to the third power gives us x cubed plus 3x squared h plus 3x h squared plus h cubed. X corresponds to a, h corresponds to b, for a plus b to the third power, minus x cubed, all divided by h. Now, with limits, what we would like to do with an expression like this is we would like to just plug in h as 0. That would make the whole thing work well, except plugging in h equals 0 gives 0 in the denominator. It also gives 0 in the numerator, which is a signal or something that tells us there very well could be cancellation. There's going to be some cancellation because we have polynomials. And, well, let's see. That's what we're going to see right now. So because the numerator is a polynomial, there's going to be some cancellation. It's a polynomial in both x and h. Okay. Now, the x to the thirds cancel out. So we could maybe skip this next line here. But I'm going to copy everything down. Okay. So I'm now getting somewhere, I think. The next thing I'm going to do is I'm going to focus on, in the numerator, there are expressions involving h, and there's an h in the denominator. I'm going to factor and cancel. So I have h up here in the numerator, and then 3x squared, so I'm factoring the h out. That leaves 3x squared plus 3x h to the first power and h to the second power. Okay, now I am just going to go ahead and cancel. Maybe not the best color. I'm going to cancel now. Okay, that's going to give limit h approaches 0 of 3x squared plus 3xh plus h squared. H approaches 0. I'll put arrow to show approach. At this point, I've been writing limits throughout. I've been writing limits the whole time, every time I copy down the expression. But once I plug in h equals 0, I'm not going to write limits anymore. I'm going to just put in 0. Once I put the number in, then I don't write limit anymore. I can directly substitute because I won't be divided by 0. So 3x times 0, that's going to equal 0, not just limit 0, it actually equals 0. And this gives 3x squared as our final answer. So there we go. Okay, this is Stewart Calculus Early Transcendental, 8th edition, section 2.3, number 31, where we find a limit and we use a binomial expansion formula for a plus b to the third power.